Now then the iPhone arrived, and again they're unhappy because the networks are completely overloaded. And one of the reasons they're overloaded is because we're using it everywhere, the phone. We start in the early morning in bed, having breakfast, commuting, before lunch, during lunch, afternoon, late afternoon, early evening dinner, late evening, and in bed again. And at a very constant rate, which is using that network. And another reason why they're unhappy is because we as engineers have failed, completely under-designed actually this cellular network. Now if we look a little bit on the statistics, we see that actually most of the time we use these phones indoors, about 80%, and 20% outdoors. I'm not saying only 20% outdoors because those 20% count, okay? So it's not just about making a good indoor system, you also have to have a very good outdoor system. Both of them count very much. Now that usage is essentially driving the capacity up in the networks, and if you look at the predictions for 2020, how much data is going to be generated over the wireless interface, it's an enormous number. It's actually more molecules than we have in the universe. So this is the number of bits being transmitted in the system per year. Okay? It's a meaningless number, really. The only thing I would like you to understand is that this goes up exponentially, and we are somewhere, well, you will see in a second, we do the calculus, we're not even visible on this chart. Okay, so we have a lot of engineering to do to make that happen. Now, are we prepared really to meet that capacity? Well, we look at our thought leaders, the IMT. I'm not sure everybody knows in this room what IMT really is. It's a kind of standards body, a thing in Geneva, you know, having good cheese and stuff like this, and thinking, you know, what's going to happen in the next 10 years, 20 years in terms of wireless capacity needs. And 10 years ago, they were designing the 4G system, or the requirements of the 4G system, and it is documented in a document called IEEE M2133, and they said, hey, to be able to meet the 4G requirements, you have to have a spectral efficiency of at least 2.2 bits per second per hertz and 1.4 bits per second per hertz of uplink and downlink, etc. Now, if you translate that a little bit to the volume of capacity you can offer in absolute terms, given a decent rollout, not too expensive, not too cheap, assuming cell sizes of 500 meters, which is very small, okay, and a spectral band of 40 megahertz, which is not too little, you end up essentially with a capacity density of 100 megabits per second per square kilometer. Now, I believe in 1998, 1999, 2000, that sounded like an enormously high number to provide essentially, you know, these type of capacity densities. But now let's do a reality check really, and I'm not sure why they haven't done it, because they could have done it in the past already. So we worked on a peak density of 8,000 people per square kilometer. So I have a table here. European cities, they don't reach that number. New York City reaches that number. Mexico, Moscow, Mumbai, etc. So loads of cities who hit that high number. So we have a need in urban environments to provide, you know, capacity to 8,000 people per square kilometer. Now let's assume only 10% are subscribed, okay? Which is not true, because today at least 50% subscribed, I would argue. Let's assume of those 10% subscribed, only 20% at the very same time need essentially capacity, which is probably also an understatement, and let's require each of them to download and upload at 5 megabits per second. You do the maths and you come up with a number that actually you should be providing close to 1 gigabit per second per square kilometer, and not what our thought leaders were saying of 100 megabits per second per square kilometer. So they got it wrong. Factor of 10. So we have 4G is not even rolled out, okay? So don't believe the news. Verizon is not rolling out 4G, they're rolling out 3.9G. LTE is not 4G, strictly speaking, okay? 4G is LTE-A, which will come probably in 5 years' time. It's a marketing gig, so just be aware of that. So not having even rolled out 4G, it's already off by a factor of 10. By the time it will be rolled out, it will probably be off factor 50, and by the time, you know, it really matters, it will be off by a factor of 100. Right, that's the situation. Now, how have we dealt with capacity increase in the past? There's a chap out there called Martin Cooper who figured out that capacity, wireless capacity, doubles approximately every 30 months. Okay, so that means since 1975, about these years, 70s, 80s, capacity has increased by a factor of 1 million. Okay, 1 million. Now let's try to break down where that gain of 1 million really came from. And if we do a little bit of crunching and historic research, we figure out that, hey, five times, a factor of 5 came from improving the physical layer. I'm not sure everybody knows what physical layer is. It's essentially the layer which is responsible of point-to-point communication. Okay, so what really matters between my mobile phone and the base station. So working on coding schemes and modulation, etc., factor of 5. Increasing the spectrum, factor of 25. And making the cell smaller, a factor of 1,600, and then comes a little bit of the rest. Right? So you understand, the biggest impact was actually simply by putting up more base stations. Not by designing a new modulation scheme, not by going from on-off keying to QPSK 16 QAM, 64 QAM, from convolutional coding to turbo coding. Absolutely negligible impact compared to making the cells smaller. Things become even more interesting if you looked at the breakdown of the costs actually, because what did it cost us to do that? Now to reduce the cell size, of course you pay. You pay for the property, for the licenses, etc., etc. For the spectrum, you pay. For doing physical layer research, you pay. We have paid thousands and hundreds of thousands of engineers of designing new codes, Information Theory Society, you know, the whole lot of them. And the actual important thing is if you do the ratio between both. So if you, I don't think it's very visible here, unfortunately. So what I'm proposing is you should actually look at the ratio of the gain versus what it costs you. And you figure out that making the cells smaller is a good deal. Buying more spectrum is an okay deal. Working on the physical layer is a really poor deal. Okay, so instead of having subsidized you know, hundreds of thousands of millions of dollars in the physical layer design, we should just have used that money to buy more base stations. All right, that's a pretty rough fact. I'm a physical layer guy, but there comes a point when you have to recognize it. Actually, we wrote a very interesting paper with one of my co-authors, Robert Heath, who's here at the university here, Angelo Lozano, Konstantinos Papadopoulos, and Rinaldo from Bell Labs. Maybe some people know Rinaldo. So it's a pretty interesting paper which we called, "Is the physical layer dead?" Okay. I wanted to put an exclamation mark actually. The physical layer is dead, but they convinced me to make it a question mark. Okay. But so just bear this in mind. Okay, it's all about impact. You can do research endlessly. There's no question about it. But if you go down to the numbers, you see where really the impact is. Now the trend is really confirmed, so that's a slide from Qualcomm or from Ericsson, I can't remember. If you look at how my capacity increases as I go from 2G to 3G to 4G, etc., I'm seeing that the delta is decreasing. Okay, going from your IS-95 system versus your previous analog 1G system, you get a capacity factor of 10. Going from IS-95 to UMTS family, it's maybe just a factor of 4. Going from UMTS, HSDPS, so the increase goes down, okay? So people work a lot on the link layers, but actually the capacity gain is very, very small. Now this is pretty lousy news. And it essentially means to really accommodate, facilitate the exponential capacity increase, we really need to change how we build these systems completely. Okay? Otherwise, there's no way we're able to build a 5G system. We will always be running behind the capacity needs, which is very bad. So the wireless communication society is always running behind the capacity needs. We always talk about Shannon. We should never be talking about Shannon. Okay? Just over-dimension the system, do something which offers so much capacity that we can run the applications we need to run on that. So we still talk about it. And spectrum is not an issue. No, it's not. No, I'll show you later. It's not an issue. And green communications, all that, power efficiency is not an issue either. Okay, I'll not show it today, but it's not an issue. An issue is how you build and put the building blocks together. So let's look at some design paradigms of how to make that happen. Number one, we have to clearly differentiate the design between outdoors and indoors. Okay? So far, cellular operators have been very good in designing a cellular system which worked really well outdoors and somehow not so well indoors, simply because it got walls, signal is shadowed, etc. So there's another movement happening with Femtocells, and I'll tell you later. So you're putting up a small base station in your home. Now that is a proper indoors design, but these guys were not very happy with doing it. So it took a long time to get Femtocell design into 3GPP community, okay? Because the cellular operator was threatened by people putting up base stations using their licensed spectrum for which they paid a lot of money, and they're not having control of it, okay? But there's no other way of doing it. And I'm putting it up these numbers here. 80% of the time we are at home, 20% we are outdoors. It doesn't mean we have just to focus on here, because you know, if you're not happy that 20% you're outdoors, you change operator. Okay, that's called customer churn, and they don't want it. So you really want to make sure that both systems are well designed and that they give similar experience. Okay, so you just don't want to download a movie indoors and not being able to do that outdoors. So that's number one. Separate it clearly and be ready for both systems. Second point, put a lot of effort on the architecture and the management of the architecture. You know, don't look at the link level. Take whatever's out there. Okay, stop designing these systems. Stop doing new physical layers, whatever. We have other problems to solve. Okay, how to put everything together, how to build a puzzle, how to make these technologies work together. So that's another design paradigm really of 5G. The third one is acknowledge that heterogeneous technologies are out there. Okay, the cellular community, the 3G community would never ever talk with the Wi-Fi folks. The Wi-Fi people would never talk with the 3G folks. The WiMAX people don't talk to anybody, nobody talks to them. So it turns out we have a lot of really good systems out there, rolled out with infrastructure, but they're just not talking to each other. That's very silly, okay? So it would be great to put it all together and have an architecture which actually is workable from, you know, from all these technologies' point of view. Another one important one is stop using spectral efficiencies. You know, nobody cares. Frankly speaking, nobody cares. That's really something, it's a design paradigm of the past. We are there, okay? Our systems are good enough, physical layer is good enough. We're very, very close to the Shannon bound, which is spectral efficiency pattern. Just stop talking about it. Let's talk about the real numbers, okay? We just don't know, as an engineer, we lose sight very quickly. What does it mean, 2 bits per second per hertz? It doesn't mean anything to us, okay? Now, if I tell you 5 megabits per second per square kilometer, now that's something you can associate with, because you're downloading things, you're uploading things, you know about the rate. Let's get talking about this. And another reason is because the moment we start using heterogeneous technologies, they will be using different chunks of spectrum. Different chunks of spectrum cost a different price. So therefore, just talking about a single spectral efficiency just doesn't make sense anymore. You know, just use these numbers. And another reason is actually a lot of spectral efficiency gets lost as you go up the protocol stack. And then cost has to be part of the whole design from moment zero. That's, you know, one of the problems probably of the past. You know, systems have 3G is in my opinion, a pretty lousy system in terms of you know, how it's been designed. It's very complex. It's very, very costly. Power control is a nightmare. So 10 years ago, I wrote the complete link layer on UMTS. It's just really bad compared to 2G. Like GSM is a fantastic system. 3G, I think, was quite a disaster. LTE is a beautiful system again. But you know, because there was different design driver, etc. So bear this in mind. We really need to actually take cost into account. Also because we are coming out of a voice dominant era into a data dominant era, which means, you know, the traffic goes up and the revenues flatten out, okay? But the cost to support the traffic actually lags just a little bit behind the traffic. That's a big problem. And the mobile operator is bearing this cost, and those who really make money out of the traffic, like the Googles and the YouTubes and the Facebooks, etc., they don't pay anything for that, okay? So things are a little bit changing now. So in Spain, Telefonica signed, like the equivalent of Verizon here, signed a deal with Google that they would pay part of the infrastructure, which makes sense, okay? You know, why should a mobile operator put in a lot of money so somebody else can actually make money out of that? So So the ecosystem is changing a little bit, but still we need to make sure that the architecture which is supporting all the data traffic is actually as cheap as possible, because otherwise it doesn't scale. So here we are. Bearing these design drivers in mind, you know, what I want to do is I want to show you from a very high level point of view. Okay, we're not going to go into great details. The design drivers are designed for an example outdoors 5G system. What is happening in terms of indoor, and then one of the big issues, which how do you manage the system, indoor, outdoor, jointly together. It turns out that self-organizing networking is a major driver in actually organizing these type of systems. It's going to be these three things really. So let's start with the 5G design. Now I worked on the 5G design since, you know, back then we didn't call it actually 5G, we called it beyond 4G, since 2007, 2008. So I got back then I got together over coffee with the CTO of Varian. We sat down and we actually did the number crunching. I showed you at the beginning that we're running short of capacity already in 2007, and that was well before the iPhone came out. Okay, so we sat down and said, let's do something about it. Let's increase that capacity. Now, one way of increasing capacity is just put more base stations, but it doesn't scale. It's very expensive. Okay, so what we said, okay, let's come up with some design principles which would allow us to build a system which performs what it is supposed to perform, deliver the data, which scales. Meaning, if we go from 100 megabits per second, 1 gigabit per second per square kilometer to 10 gigabit per second per square kilometer, we still can do it, whilst cost is reasonable. Okay, cost is good. So we wanted bits per second per square kilometer per dollar. That is something we really wanted to get sorted. So we started working on that, and we applied a little bit on the architecture, something what I call, you know, the water filling applied to equipment placement and its choice. Now, water filling, I'm not sure you're familiar with that, but in the MIMO theory, when you have multiple input antennas and multiple output antennas, if you do a single value decomposition, you get, you know, a set of eigenvalues, and the theory tells you to get the maximum capacity out of that link, you have to put most of your power into the good link. Okay? Less power in the less good link, etc., and the least power in the worst link. So instead of equally distributing your power over all your capabilities and possibilities, put most of your effort into the, you know, into the one which gives you good gain. Now we applied the very same thing. So instead of having a lot of base stations all over the place, we decided, okay, let's take one base station which is really powerful and it's really expensive, okay? And then we have loads of small base stations around which are very cheap. And it turns out that this actually does the deal. So, you know, having one expensive and a lot of cheap one around is what helps. So this is what we did here. Then we applied a very aggressive spatial reuse, because at this very expensive base station, which we called the hub base station, we had a very narrow beam. So we had an array with 48 beams, okay, all dual polarized. So that means, you know, we had an extraordinarily good spatial reuse over the whole city. Then we were the first ones to recognize that most likely, you know, if my hub base station communicates with my cheap devices, you know, you have a capacity problem on the backhaul we are creating, okay? So we were the first ones to start actually advocating the principle of a joint access and backhaul network. What does it mean? You know, the link from my mobile phone to this cheap base station, and from the cheap base station to the powerful hub base station, suddenly was belonging together because they're using the very same resources, so you had to optimize that together. So therefore we did that. And we advocated for an extraordinary aggressive reuse or use of licensed and license-exempt technologies. Okay, there's a very big difference between those technologies, but they're out there. So the licensed technology is 3G technology, WiMAX technology, the 3G technology, cellular technology in general. The license-exempt technology, it could be Wi-Fi, could be WiMAX, could also be a 60 gigahertz microwave link, etc. So if applying all these principles, I don't want to go into too many details here. We came up with that architecture here. So you have the city, you put up that beast here with 48 beams going around, very powerful, and then that one did it? How do we do it from the frequency point of view? So we have various links here. So that is my hub base station. I put here the antenna pattern on top, and it is communicating with the access base station using different types of links. So it could use the license link, the L. L stands for license. So it could use a 3G link to get there, and my access base station would also use a license link to the user. Could also be 3G. But my hub base station could also use licensing sandbands, so WiMAX link, 5.3 gig. Okay, that's fine. Or it could use a gigahertz link, so a microwave link. Microwave is a good choice because since we established that cells are getting smaller and smaller, actually it turns out that every single base station sees any other base station. So if you really pay attention in Austin, density of your wireless equipment, of the mass of the cellular is so dense that any base station sees any other base station. So we worked with an Israeli company, came up with a fantastic microwave link solution here, which would establish eventually our backhaul. So that's it, no magic. I told you we're not doing any breakthrough in terms of element design. We're not doing any new physical layer, nothing new. We just put it together such that it works and addresses the capacity we need. We started doing a lot of planning exercises, how to plan the technologies. You see a lot of degrees of freedom. So Alvarian was very much in favor of doing that in a deterministic fashion. Other people were not so convinced about it because city changes, maybe a city is not so regular. Manhattan might work, Barcelona might be like this, but Austin has maybe a little bit, the streets are very regular. So we started working also on autonomous algorithms. I'm going to tell you actually at the end of the lectures there's some choices of that. So just to tell you that we did it, okay? We did the whole design of that, we did the protocols, and we simulated it. So we put out a hub base station, some access base stations here, all well done, aggressive frequency reuse. We even had to redo the channel models, okay? So all the 3GPP channel models hold for a certain beam width, but because the beam width was so narrow, it turns out that the channel models changed completely, okay? So we had some people redoing the models to really get a more realistic picture. It turns out, I won't go into details, but it turns out, that we were able to offer the 1 gigabit per second per square kilometer, at least from a simulation point of view. So that was very encouraging. And we went to the standards buddy, okay? So we went to standardize the whole architecture. So it's now standard, the 2 standards document in ETSI. ETSI Broad, the broadband radio access networking. ETSI is quite progressive in the sense that it would accept architectures where actually different technologies come together on a single page, which you would never see in IEEE or in 3GPP because, kind of competing, whatever, the ecosystem is very different. So ETSI is very good in that. ETSI, of course, doesn't specify the actual protocols. It doesn't tell you, which physical layer to use, etc. It specifies blocks, interfaces, control primitives, etc. We have done that, so you can download that document. So that architecture is out there and approved by the industries of ETSI. And then we started building it. Okay, we thought, okay, you design it, you standardize it, let's build it. So we built the beast. That is the hub base station, which is, offering the really narrow beams here. It's a British company called Cobham, which came up with the design. We built the access links. Alvarian offered the SISO link here. CTTC, MyForks, they built a very powerful MIMO closed feedback link here. So we just put it all together. And we had also the Cyclo solution, which is an Israeli company offering an extraordinary cost-efficient 60 gig backhauling solution and extraordinary high data rate. That's a beautiful thing about 60 gig. You just don't care about capacity. It's so high, it's just like a black hole. It's just like a fiber. So whenever, two links have line of sight and it works, you don't worry anymore about this. So we put it all together and we went to trial it. Okay, so we wanted to show to the world, yes, we can do a beyond 4G system, and we did that in Tel Aviv in April this year. So we put up actually 2 hub base stations. In the end, only one was active here. We had a few access base stations all over the place. That is Varian's headquarters there. And we put it all up, nice and neat. And that's an example down there of an access base station which was mounted below rooftop. There's a lot of cell planning done on the Varian side with their cell planning tools, put it all together. and put the antennas there. There's the hub base station here. You know, a lot of equipment there on the roofs, putting it all up. And then we started trialing it. So we had quite a lot of press actually that day. So we had people driving around in the cars, downloading movies like crazy. Everybody was going there. So there was mobility. There was, you know, it was a proper system. It was working actually. So we had built, you know, within 2 years, a system which was already 10 times more powerful than what 4G was requiring to do. Okay, so we did we did a lot of analysis also in terms of data rates, throughputs, you know, all the statistics is all available on the design website, so you can get all that information. So we really made that happen. Okay, just to give you an idea that, you know, four years ago we started working on this beyond 4G. Everybody now is talking about 5G, so we did the architecture standardized, proven it works. It's very scalable. So if you want to go up from 1 gigabit per second per square kilometer to 10, you just squeeze a few parameters. You just put up more access base stations, the cheap ones. Okay, that's the beauty of it. You scale a little bit with bandwidth. All this was done with 40 megahertz of bandwidth. So if you go up to LTE-A bandwidth, which is 100 megahertz, you automatically get like double or 2.5 more capacity. So it's a very powerful, very scalable, and very cost-efficient system. Really, we build that. Okay, so much indoor, outdoors. Let's come to the indoor design. And the indoor design revolves really around Femtocells. Okay. Before I tell you what Femtocell is all about, let me place it in the ecosystem of small cells. Femtocell essentially means, you know, it's a small coverage, cell coverage. And Femtocell is not the only cell. There's a so-called remote radio head. What is a remote radio head? Remote radio head is if you have your base station somewhere in the building, it might be on the roof, but it has an RF cable connecting the base station with the antenna to somewhere else. So we could put an antenna right here in the room, but it's actually controlled by a base station on the top. Okay, that's called a remote radio head. We could have a few of them. A relay is something which is typically controlled by the base station. So you may have a macro cell base station which is communicating with a relay, giving it instructions to do so. It's not really autonomous. It is, but it's also not as stupid as just a remote radio head. And then you have a picocell, which is a small cell placed by the operator. That's very important. So, you know, if an operator realizes that there's a bad coverage in this building, they may just come in and ask, hey, can we put up a picocell here to offer the clients essentially a good radio coverage? How do they realize it? They realize it because they have a lot of drop calls. Okay, somebody, you know, Freescale people get into the building and suddenly the calls drop. So the guys know, hey, there's a problem. There's a coverage problem. Call up, come here, put a picocell, do all the planning, it all works well, all is solved. In contrast, maybe Freescale says, hey, I want to offer to my employees something which goes beyond just a simple picocell. I want to put up my own base station, offering whatever it is. Maybe, you know, putting a capacity and coverage up where maybe you don't want anybody to go in. And that is really what the Femtocell is about. This is like a base station which is administering essentially a cellular system, but is placed by the consumer. So it's a consumer product. Okay? So going from a business, commercial product, but suddenly you hit the consumer market, which is quite a challenge. It's a totally different vertical and a little bit of a nightmare to the operators. Now, differentiation. I put this slide up so just, you know, for you to see the difference between Wi-Fi. All of them operate typically in indoors, you know, environment. Wi-Fi, picocell, Femtocell. Now, if you look at the picture, they all look the same, right? It just turns out that technology is converging very quickly. Actually, if you look inside, an LTE-A or an LTE Femtocell has more or less exactly the same chips inside as a Wi-Fi, all right? Almost precisely the same, at least from the physical layer point of view. And of course, the very same as the picocell. The only difference is that, you know, picocell is put up by the operator, everything is optimized, it can transmit a little bit higher at higher transmission power, but otherwise, things are more or less the same, and, you know, things are converging over time. They're actually converging because Wi-Fi comes out of the IEEE family, and IEEE has always been very good at delivering high data rate, okay? Femtocells and picocells come out of the 3GPP family, which always have been very good in delivering solutions which are good for roaming, mobility, handovers, etc. And now it turns out that femtopicocell is pretty static traffic, so they're converging naturally to this solution, which IEEE has been outlined. Now, Femtocell opportunity, we had a whole day yesterday about the smart home. Femtocells are really, in my opinion, at the center of it. You know, there will be Wi-Fi, there will be a femtocell. It offers you just really a very seamless experience. So it means you have your own cellular base station at home. It means, you know, you come home, you can just talk, you know, suddenly to your own base station. You don't need to connect to the macro cell, which saves everybody a lot of power. You can continue downloading movies, whatever you did outdoors, you do it indoors, okay, with your own cell. You don't have to change interface. You don't have to switch from cellular to Wi-Fi. It's completely seamless. And the beauty of that technology is it's actually controlled. You control interference. Okay, that's one of the biggest advantages over Wi-Fi technology. Wi-Fi, you may have 16, 20, 100 Wi-Fi stations in visible range. They're all competing. There is no control over who gets access and when. There's some rules of best practice, but there's no real radio resource management that's taken care of. Femtocells are very different. They help also reducing customer churn because coverage is simply very, very good. They also help offloading traffic. So if naturally, you know, instead of using the macro cell interface, you will use essentially the femtocell interface like a Wi-Fi to offload this stuff. And there are some energy savings in for all because you're communicating over much shorter distances. Femtocells apparently are very appealing. So in the United States, 38% of the people said, hey, that's a cool product. I would use that. It's a good market share. Ones who most convinced about it is actually the Chinese, which is a little bit surprising because I'm not sure you travel to China, but in China, the macro cell coverage is just really ubiquitous. No matter where you go in the deepest basement of whatever building, you get always that five-star cell coverage, you know. So one of the big arguments for using actually Femtocell is you get good coverage even in the basement. But nonetheless, you know, the Chinese love it. The general the market loves it. The ecosystem is very mature, so you see a lot of companies out there, and you have to think that all these companies have their CMOs doing all the calculus whether it's good business to do femtocells, and it turns out it is. So you have ecosystem people who provide the components, the access points, core network components, end-to-end solutions, etc. So it's a complete system right now, and being rolled out as we speak by AT&T, Verizon, Orange, you know, Japan, Beeline in Russia, etc. So it's a lot of stuff happening. Now, when it comes to business modeling, there are essentially two approaches and one singular case. Okay, so typically what you can do today is I'll talk about your country here. So Verizon says, okay, you go to their shop, you buy a femtocell today, you can do that. Okay, $250 and it's yours. That's it. End of story. Go home, connect it to the Ethernet, to a fiber optical, and you have your small home cellular system running up and running. Okay. Now AT&T is doing the very same. Sprint has a different vision. Sprint says, okay, if you buy it from me, you get it for zero cost, but you got to pay me a monthly retention fee of $5 in addition to the price planning I'm offering to you. Okay, so it's different CapEx versus OpEx model. All countries are more or less the same, so trading one or the other, except SoftBank in Japan. SoftBank in Japan is offering the whole system for free, completely. Okay, so you go in the shop, you get a SoftBank femtocell for free. You don't pay any fees, monthly fees. It's just a complete free solution. So they do the money clearly in a different way as all the other operators. And they're scaling up, so it seems to work. So their market prediction is positive. The number of femtocells to be rolled out is very large. Now, from a technical point of view, who's driving all that? It used to be for quite some years now, since 2007, an institutional alliance called the Femtoforum, which rebranded this year, at the beginning of this year, to the Small Cell Forum, simply to address, you know, the smaller cells out there. It's manufacturer-driven, so it was not cellular operator-driven. Cellular operators were very afraid of femtocells because it means creating a lot of interference, which we don't control, and which has a very big impact maybe on my macro cell performance. And so they were a little bit reluctant of doing it. But finally, femtocells have entered 3GPP. 3GPP is essentially, you know, operator-driven. And you will see in the specifications a notion of H, E node B. So that is H for home. Okay, E node B is a base station, so it's a home base station. So first time in the architecture design appears essentially the ability to plug in my Femtocell into the 3GPP architecture. So there are a few others like IEEE and Hotspot and the GSMA working on the Femtocell. So this is really taken off because people realize you can solve the indoors capacity problem with the Femtocells. Now from a design point of view, there are quite some challenges actually. First one is to really get the cost down. Okay, you really want to make sure that the Femtocells are very cheap because it's a consumer product. Okay, so it's not anymore an operator product, a business product, it's a consumer product. You want as many people as possible to buy essentially your device. So it has a lot of implications on the power amplifier design, etc., because suddenly you have to sell a base station with the capabilities of a really expensive base station, but at a consumer price. So there's a lot of design going into that. You have to manage interference. Interference is a big issue. We'll talk about this in a moment. You have to maximize capacity, otherwise it doesn't work. So loads of challenges here. And then suddenly, when you start offering that an enormous amount of capacity, backhaul becomes an issue. How do you offload all this traffic through your backhauling system? And actually, one of the reasons why Vodafone in Spain, for instance, has been bringing a little bit, slowing down the rollout of Femtos is because the backhaul they had was not prepared to offload that enormous amount of data traffic. So this needs to be solved. And of course, we need to work on a very, very good architecture. So the only thing I want to talk about today with you is a little bit the interference, because that's something which operators are really afraid of. And the interference which may occur can go either way. So either the Femtocell is creating interference onto the macrocell or the macrocell on the Femtocell. But there's one case which is really important, which everybody's afraid of, is when the Femtocell creates a lot of interference in the macrocell. Okay? It can happen when a macrocell base station tries to communicate with a macrocell using a downlink, and at the same time a Femtocell is communicating with its Femtocell using the downlink. Okay? Because the power which this Femtocell transmits might be just big enough to actually silence the signal which comes out from the macrocell. So that is something operators are really afraid of. What's a practical example? We have a Femtocell right here in this room is serving a very specific set of people. The other set of people is not allowed to use a Femtocell, okay, because it's not an open Femtocell. So the other set of people has to communicate with the macrocell. Now, they are both using the very same spectrum. They're not coordinating so far. There are no specifications how to do that. And it turns out, you know, that base station, Femtocell base station, is transmitting quite a high power to the Femto users, and is completely silencing or interfering with the macrocell signal. So half the room is very unhappy, and you leave the operator because you think it's an operator problem, but actually it's a Femtocell problem. So let's focus on that one and see a little bit what can be done. Now, since release 10 of the 3GPP specs, the community realized that one way of doing this is by stipulating a proper intercell interference coordination. That means you're trying really to coordinate interference between cells, and you can do that either in the time domain or in the frequency domain. Okay, that's basically what you can do. So you have, as an example here, the carrier 1 of the macrocell and the carrier 2 of the macrocell. It's communicating with the users, and you have essentially carrier 2 being used by the Femtocell, but carrier 1, you are asked, the Femtocell is asked not to use that carrier because it's interfering too much with the people which are here. So you're silencing it, you're coordinating the transmission between macrocell and Femtocell. And the same in the time domain. So you can say, okay, there's a particular time slot, my Femtocell is not allowed to communicate because there's a lot of interference. At another one you can do it, etc. So this is essentially how it is done these days. You protect resources, important resources, the macrocell resources, and you do that type of ICIC. And this is how it looks like, essentially, my LTE and LTE-A data packet. It is typically preceded by a control channel. Okay, so what you have is time here. So these are my OFDM symbols. That is frequency. And you can see that my first symbol is a control channel symbol. My second and third one can be control channel, don't have to be. And then comes my data path. Okay? So a lot of emphasis in the community has been put on how do you coordinate interference for the data path. very little has been paid to actually how do you coordinate interference on the control part, okay? Because the silencing I've shown you has been done for the data, but it's not done for the control. The problem is if you lose the control data, you lose the packet, okay? So what you actually have to protect is the control stuff. So we worked a little bit on that, and to understand what we did is actually maybe the only example I'll give you today is you know how this control packet is actually the symbols are being composed. So the time goes down this direction, that is my frequency domain, and a control packet contains essentially three indicators, three channel information. First one is the control frame indicator, which tells you how the control channel is composed. Then it contains all the downlink information of the cell, so what cell ID it is, PCI, etc., power control information, and then the feedback on the uplink communication, so the hybrid AIQ indicator channel, whether transmission on the uplink was successful, etc. So it's pure control information, no data, all right? Now it turns out that the placement of that data, that control channel, is deterministically determined by an ID, which is the physical cell identifier, PCI. It's a very important notion in cellular design. PCI, every single base station has a single PCI. Unfortunately, there are not too many of them, okay, because they're being reused all over the country. But essentially, the moment a base station is assigned a PCI, it determines where the control symbols will be allocated in the control channel, okay? So what we propose to do is to say, okay, a femtocell, instead of randomly choosing a PCI from a set, and therefore randomly placing these symbols, and therefore having a good chance that they will collide with my overlaying macro cell, we said, okay, let's do that intelligently. So the femtocell ramps up, it listens into the medium, it decodes the presence of a macro cell, it decodes the PCI of the macro cell, and explicitly chooses a PCI which is different from the macro cell, okay? In such a way that the control information, the control symbols do not collide, right? So you have a completely backwards compatible solution, very simple, and minimizes interference between macro cell and femtocell. Another thing we worked on, and Qualcomm came up with that, is to use beamforming actually at the femtocell. So it turns out you can do quite some intelligent beamforming, and if you are beamforming at the femtocells, what you're trying to do is to beam steer away from the macro cell user. Okay, so get the least possible power to the macro cell user, and most of that actually to the femtocell user. And we see quite a lot of gains, up to 50% improvement of the macro cell user, whilst the femtocell user only suffers 5%. So it's a good deal. Okay, so coming to the third part now, you know, the closing part of the presentation is, you know, we have designed now the outdoor system, we've designed the indoor system, now we need to manage that, okay? So it turns out that's actually one of the most tricky things, how do you manage that? And you realize that if you look at the whole, you know, ecosystem of technology, you have a lot of stuff out there, okay? You have a few macrocells, more microcells, even more picocells, even more femtocells, even more sensors, machine to machine, device to device. Put it all together, suddenly you have a system which is extraordinarily complex, some of them interfering, some of them cooperating, etc., etc. Now, how do you manage that type of system in an optimal or close to optimal way? Well, it's very tricky, it turns out, okay? You figure out very quickly that the so-called degree of freedom of the system is extraordinarily large. A degree of freedom is an ability to tune something. Okay, so how much power do you allocate, which frequency do you give, when can a user transmit, etc. And as we move on from generation to generation of cellular systems, from GSM to edge UMTS, HSP, LTE-A, this is what I showed you today. It turns out as I go up the generation, I always have about an increase of 100 in terms of degree of freedom. Okay? That means compared to my GSM system, which was pure, simple, easy to manage, comparably, today I have a system which is, you know, 12 orders of magnitude more complex to manage. And this is only increasing. So how do you do that? You can't do that. As a person, you can't do it. As a computer, you can barely do that. So we need essentially really SON, self-organizing networking, to make this happen. And SON helps in two things. So this is where machines are very good. It helps in doing boring jobs. Okay, manual labor, simply you have to do Very few people know that, but when you put up a new base station, actually engineers have to go there. They have to check how whether the software is actually up to date. They do an inventory check. They have to program all the PCIs, all the IP addresses. They have to establish tunnels. So it's a very elaborate procedure. You know, machines can do that very quickly, very efficiently. And then someone helps really well where people just cannot help. Okay, things which happen too quickly, which adapt too quickly. So you have to really react as a machine. This is where essentially SON can help the cellular design. Now, from a networking point of view, it can help at the automatic planning. It can help with the self-configuration when you ramp up the system, self-optimization when it runs. So it might be a sports event, so the system needs to optimize. The capacity in day and evening is different, so therefore it's optimizing all the time. It's troubleshooting. There's a problem here. There's one sector going in an outage. How can I do that? So these type of functionalities, you know, before it was human labor, and now we would like the machines, the self-organizing networking, to take over. What do you trade, really? You have different self-organizing mechanisms placed at different places, and what you're really trying to do is you know, to see what is applicable where. So you can apply your self-organizing networking mechanism in a really central fashion. So you have a central server which is taking central decisions and saying this cell now does that, this one does this, etc. Or you can start to distribute it. Okay, so two neighboring cells are trying to figure out what to do best. Or you have it localized. A single base station just says, okay, I want to do that because I think that's the best for the cell. What you're trading here, as you go from centralized to localized, you can do things much quicker. Naturally, because, you know, centralized, you need to collect all the information, you need to take the decision, and you need to sprint it back to the Femtocell, to the access point. Also, you are less prone to single point of failure, so that's essentially what you're trading here. On the other hand, if you go centralized, of course, if you have more information, you can take better decisions. So therefore, these algorithms naturally will probably be better in terms of optimal capacity optimal. So what people do today is, what is done localized is very, very quick decisions you have to take at rate resource management level. Okay, how much power to this user, when to transmit, what modulation index, etc. That's done locally. Distributed is everything which is related to two neighboring, three neighboring cells, a handover decision, load balancing, etc., etc. Whereas a centralized is really a global thing. You know, the cell identifiers, general, you know, self-configuration parameters, etc. So this is what is happening today as we speak, NGMN and 3GPP. Now we decided to work in our center specifically on some very specific self-organizing mechanisms which come out of the cognitive family. Okay, so we really believed that, you know, the only way of ramping up a system which has a degree of freedom of 10 to the power 12, 13, 14, 15, the only way of doing it is to put in some intelligence in there. So we have a very big community, the artificial intelligence community was working on these type of problems, and they came, you know, with a whole framework, the cognitive framework, which is essentially, you know, you get data, you observe things, you take it, you learn, you take an intelligent decision, and you execute the decision. You observe, learn, take a decision, execute. So it's a circle essentially. Okay. Now, what we observed is that it's a fairly academic circle. What does it mean? You know, that if I go to Verizon and tell them, hey, put in a cognitive system, you know, they wouldn't get it because they understand that these type of systems have big problems of convergence. They're not very stable. They're not very precise. That means, you know, sometimes I take a good decision, sometimes I take a bad decision. So they're not very industrial. Industry wants something, you know, which works most of the time. So we said, hey, why don't we look into a principle which I call the decision, the dositive one, which comes from Latin docere, to teach, okay? Where instead of everybody learning independently, people start to teach each other. It was inspired essentially by the pupil, you know, teacher society we are driving, where essentially a generation of teachers is teaching pupils and they become teachers, etc. And it turns out for the machine, this worked really, really well. So what we said, okay, a machine which is quantified to be very intelligent is becoming the teacher for machines which are not so intelligent, and they're distributing the know-how in the system. And it turns out that that type of system has started becoming extraordinarily stable and very performant. So I'm going to show you in a while how that works. The very specific artificial intelligence mechanism we use comes out of the machine learning community and is called, it's a reinforcement learning type of mechanism called Q-learning. Q-learning is a little bit like we operate as humans, okay? There's no difference really. Q-learning has an input and an output, okay? An input and output is related by a matrix, a table, all right? So let me exemplify this a little bit. So we have an input state, maybe as an example, two states. I typically take the example of a baby learning or a child learning not to cross a street when the light is, pedestrian light is red. So we have input, the light is red, light is green, and output we have standing or walking, okay? So now as a child grows, at the beginning it takes some very random actions, okay? It doesn't understand that, you know, red light is bad, green light is good. So it just walks over the street when whatever happens. Now if there's a red light, the mom says, you know, that's a bad thing to do. So essentially that value which connects the red one with walking becomes, you know, a value which is, has a negative reward, punishment, and whereas when the child walks over when it's green light, you know, that becomes essentially a value which is positive. So this is how you train the system, okay, more or less. And we do the very same in our cellular design. It's the very same story. So we have as an input the power, maybe the interference levels, the capacity, when do I transmit to whom, what type of resource, etc. As an output, I have, you know, the capacity achieved, etc., etc. So the system learns on the run. It's clearly very complex. Okay, these tables can become very, very big, and we have mechanisms of making them smaller. But it works the very same way as we humans learn on the run. So we use that type of system, and the intelligence is in these values, okay, in these table entries. These are the neurons, really, of the whole system, like we have them in our brain. And how do we do the decision? So how do we do the teaching? Well, we exchange neurons. We don't exchange results. We don't exchange observations, okay? We exchange literally the table entries. So if I know that one machine is more intelligent than another machine under very similar operating conditions, I say, hey, give me the whole row of table entries. So I don't have to learn this, you know, going by green over the street or stopping at red. I don't want to learn this again. You know, just copy these values and give them to me. And we distinguish essentially two decision methods. One is the startup decision. That means specifically applied to the context of femtocells. It means a femtocell is being switched on, and instead of learning itself, it would query its femtocell neighbors and say, hey, give me the values which you have learned, and it would just take those values. On the other hand, the IQ-driven one is a dynamic update. So we always try to figure out who's the most intelligent femtocell in the room, in the building, and you would exchange essentially knowledge on a regular basis. And that is the performance. You know, a few graphs just to verify our findings. Actually, in this graph, you don't really see what I'm plotting here is the macrocell capacity, so what worries the mobile operator, versus the active femtocells, okay? Now, what an operator would not like to see is that the number of femtocells increases to be active, that the capacity of my macrocell user goes down. They don't want that, because it means a very big impact on the macrocell network. And we have different methods here. There's one method which is really lousy. There's another method which is typically being used. That's the deterministic method, which we see that the capacity is decreasing in the macrocell network as we start switching on more femtocells. And then we have the machine learning approaches, all three of them, the traditional cognitive, and the two dositive I just explained to you. And it turns out that capacity in the macrocell is almost untouched. Okay? No matter how many femtocells we switch on, the system adapts in such a clever way that capacity is barely jeopardized. And we all see that they're actually performing all the same. However, if you start looking in terms of the convergence precision, meaning how well do my algorithms converge to the mean, okay, to the average, you see that my dositive ones have a standard deviation which is much smaller than my cognitive. So it means that over time, you know, as you see how capacity proceeds, cognitive algorithms, they converge in average, but in reality, they're oscillating quite a lot. And nobody would tell you that, okay, because everybody's just plotting the averages. This oscillation is not good, okay, from a stability point. Now the dositive one, first of all, converges quicker, and then it oscillates significantly less, so it outperforms really the traditional cognitive one. And we see that in this graph here where I've explicitly put the time series. So over time, you see the blue one is the cognitive. It takes its time to converge, and it's just oscillating really crazy. And the dositive one is converging pretty quickly and at a very high precision. So that's already in industrial design. And in fact, you know, the standard, the ETSI brand standard I'd shown you before, we put in the cognitive and dositive mechanisms into the standard. So that is being standardized today. So concluding really, future challenges. I think for the outdoors guys, for the outdoors 5G design, we have to recognize that really capacity requirements were really far off reality and will likely be far off reality for the future. So this is something we really have to take into account. Let's design a system which is really by a factor of 100, by a factor of 1,000 better than what we have today. Okay, so the architecture I'd shown you does that precisely, and we haven't not worked on the file layer, very little. Okay, we have done a little bit, very little. We've worked really on how to put it all together. We worked a lot on the organization of that, the self-organizing networking, and came up with that architecture. It's agnostic, whether it's WiMAX, whether it's cellular 3G, etc. You can plug in whatever you want. And it's really cost efficient and operates really in an autonomous fashion. Now, in terms of Femtocells, the future is holding a few interesting developments actually. So today we talk about standalone femtos, meaning everybody buys its own femtocell. The near future will have network femtos. Actually, at CDDC we have a whole test bed of network femtos, meaning an enterprise, free scale, whatever, the airport will buy not one femtocell but loads of femtocells, and suddenly you can do a lot of interesting things. So you can do load balancing, you can offload traffic, you can route traffic, etc. So the network femtocell is starting to become a very interesting notion in the community. And then something interesting is also happening that people start talking about the outdoors relay femtocell and a mobile femtocell. Okay? Outdoors really means it's different from a picocell. Okay? Picocell is actually operated by the operator. Okay? So an operator sees that downtown Austin there's a capacity problem, so it puts up a picocell. Now, the femtocell is different. Austin suddenly decides it will offer its employees the ability to have a better data service or whatever. Okay, so it starts deploying, it starts buying femtocells and deploying them all over the city. Okay, so that's the type of thing which is coming here, and of course it has a lot of challenges in terms of interoperability, the theories, etc., etc. And the other one which is interesting is in the mobile, like trains, buses, airplanes, etc. Turns out it's just much easier to handle handover operations and all that, having people associated to a femtocell or a single access point rather than having 20 people hand over from cell to cell. So the signaling traffic is significantly reduced, performance is improved, etc., etc. But if you want to make it backward compatible with current solution, they're running currently quite into some troubles from a 3GPP point of view. So right now, as we speak, they're discussing how to standardize the mobile femtocell. But it actually rose a lot of interest in the industrial community. And just really to follow off, to finish that off, I think what is really important for the femtocell whole ecosystem is the self-organizing networking. I think that will be really crucial. There's a lot of startups now coming out of this domain, in Silicon Valley in particular, which really deal with the self-organizing networking problem, because it's a problem. How do you manage so many degrees of freedom? And the business modeling, I think from a femtocell point of view, is not clear at all. Maybe we need something like FON. I'm not sure anybody knows what FON is. It was founded by an Argentinian guy who lives in Madrid. It's applied to femtocells today. So, to Wi-Fi stations today. So what you do is you buy a little dongle, you put it into your Wi-Fi box, and it actually acts as a proxy point for letting other phone users use your Wi-Fi. Now the advantage of this one is it's better than just giving a password, okay? Because you can throttle people, you can tell them how much bandwidth they have with respect to you. There's much more control on that, and I think that's the whole business point of that. So you pay a monthly fee. Maybe something that could be replicated with the femtocells is a nice trade-off between open and closed subscriber groups. So we'll see what will emerge over time there. So That's really it from my end. Thank you very much for your attention at that time of the day. Thank you.
Any questions? Yes.